Hi guys, I want to talk about 5 electron pairs in VSEPR geometry today. So VSEPR stands for valence shell electron pair repulsion, and when you have 5 electron pairs or 5 electron groups, we're talking about kind of bonded atoms or lone pairs around a central atom, then that gives you what is called trigonal bipyramidal geometry. Trigonal bipyramidal, and we'll kind of talk about why that is. It sort of looks like this guy here, and we'll use that as sort of a model for each of these different options. Now with VSEPR geometry, you have an overall geometry, the VSEPR geometry, the electron pair geometry, and within that geometry you have different shapes that are possible depending on the ratio of atoms to lone pairs within the structure. So the number of molecular geometries that you can have for a given VSEPR geometry is n-1. So if I have 5 electron pairs, that means that I have 4 options that are possible. And so let's start with the first one, which is where I have 5 atoms and no lone pairs, and then we'll kind of build from there. So a good example of trigonal bipyramidal geometry is one of my favorite molecules, which is phosphorus pentachloride. So the best way to do these is to start off with the Lewis dot structures. So we need to figure out how many valence electrons we're working with here. So chlorine has 7 valence electrons, times 5 is 35, and then phosphorus has 5, so that gives me 40 electrons total to play around with. Now phosphorus is first in this and wants to make the most bonds, so in our Lewis structure we're going to put it at the center and attach all of my chlorines to it. Now this often feels weird for students because already I've broken the octet rule, and students hold the octet rule dear to their heart. So this already feels a little bit weird, but it's pretty. It looks like a star. Nothing to be scared of. So we have 2, 4, 6, 8, 10 that we have used in bonds. So that gives us 30 electrons total to work with for my outer atoms. So now I need to fill in the valences of each of the outer atoms, and if I have any left over, I'll stick them on my phosphorus. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So I've used up all 30 in filling the valences on my chlorine. So I don't have any left over. So my phosphorus is good, my chlorines are good. Now this is a valid structure even though it breaks the octet rule, because if I was to look at the formal charges on everyone, they're all happy. So there's no formal charges on this structure. Even though the phosphorus has 10 valence electrons, it's still a valid structure and it will exist. So then in order to figure out its geometry, if this is my Lewis structure, which already looks kind of weird, then I need to figure out how many atoms and how many lone pairs I have on my central atom. So I go to the central atom, I say that I have 5 atoms, no lone pairs, and when I add them together, then I end up with 5 electron pairs total. So that 5 electron pairs means that I have trigonal bipyramidal geometry overall, and so I'm going to draw this thing like a trigonal bipyramid. So I have my phosphorus at the middle, and then I know that in a trigonal bipyramid, if you've seen my other VSEPR videos, you know that there's kind of a straight line. There's kind of 2 parts to it. There's the axial part, which is a straight line. So I have atoms 180 degrees from each other. And then the middle bit, the equatorial bit, is a trigonal plane. So if we look down down the axis on there, then we can see that we have that kind of Mercedes-Benz symbol look. So if I'm drawing this thing, I'm going to draw it with this kind of orientation where these 3 atoms are in the same plane as the central atom. Okay, so I've drawn these guys. Then if I'm using this as an orientation, this one's coming out at you, this one's going back into the paper. So the way I represent that on a 2-dimensional surface is by a big blocky triangle here. There, its base comes out at you in 3D. And then this one, that's base goes to the tip with kind of those hash marks there. So this and this represent the same 3-dimensional structures. So I'll stick that off to the side. And if I'm thinking about angles, which I always am because this is geometry here, then we know that these are right angles. So this is a 90-degree angle, which means the angle here is 180. And again, that position, these are called the axial positions. And then the chlorines in my equatorial positions, like equator, are all this trigonal plane. So the 90-degree angle is with this and the axial positions, right? So I have a 90-degree angle between this guy and this guy, but between each other, around this center bit, we have 120-degree angles, just like a trigonal plane. So we have kind of two different angle types, or three different angle types if you want to think about it that way, between the different combinations of chlorines in a trigonal bipyramid. Now, as we've seen with other VSEPR structures, the geometry overall is a trigonal bipyramidal geometry, and the molecular geometry, or the shape, and I usually will just kind of call it shape. So for the rest of this video, we'll just call the molecular geometry the shape, which recall is the position of the atoms, or the position of the atomic nuclei on a structure. This is called a trigonal bipyramid, or a triangular bipyramid. Trigonal. So I like to say that the geometry is trigonal bipyramidal, kind of using it there as an adjective to describe the geometry, but that the shape itself is a trigonal bipyramid. And if we kind of look at the lines here, you can see it in the three-dimensional structure, but sometimes it's hard to tell with a two-dimensional drawing. So I like to kind of draw in the lines because I think that helps to show the three-dimensionality of it. So here's my trigonal bipyramid. It's two pyramids that are stuck together at their bases. And that gives you this guy. Okay, so let's look at some other options now that we've thought about angles, because the angles aren't going to change. It's just a matter of kind of their position on the structure itself. So let's talk about 4 bonded atoms and use sulfur tetrafluoride as an example. So sulfur has 6 valence electrons, and then my fluorines each have 7. So I have 7 times 4, which is 28, plus my 6 gives me 34 electrons. So my first step is to draw my Lewis dot structure. Dun, dun, dun. So now I've used up 8 electrons total. So that gives me 26 to play around with. Now I'm going to put those 26 around the outer atoms. So I have 2, 4, 6. That fulfills the octet there. 8, 10, 12 fills the octet there. 14, 16, 18, 20, 22, 24. So I've used up 24 in filling the octets on my fluorines, and I have 2 electrons left over. So because my outer atoms are good, I'm going to stick it on my central atom. And now I've used up all of those valence electrons. So I'm going to highlight this guy here, because now in our accounting, we're going to say we have 4 atoms and 1 lone pair on my central atom. So we're always doing accounting for geometry based on the central atom. So that gives me 5 electron pairs total, which means that I have the trigonal bipyramidal geometry. So I'm going to draw this like a trigonal bipyramid. So the tricky part is I need to know where to put my lone pair. I kind of have 2 options. I could either take it from the axial position, so I could take off one of these guys, herp, and then it would look like this. It's just kind of silly looking. Or I could take it from the equatorial position, which would make it look like this. And if you look at the difference between the two, kind of this guy versus this guy, you can see that this one's a little more spread out, and that kind of puts the R in the VSEPR model, right? R is for repulsion, valence shell, electron pair, repulsion. So I'm going to take it from that equatorial position because that spreads out everything else a little bit more. It kind of looks more spread out that way. So I'm going to draw it like a trigonal bipyramid with my sulfur at the center. Here's my fluorines. I'm going to put my lone pair out to the side. That's this guy here, which means that one of them is coming out at you. And one of them is going back into the page. This guy. So these guys are all in the same plane. If we look at this thing then, it's no longer a trigonal bipyramid, although it has trigonal bipyramidal geometry. I actually love the name of this shape because it's aptly named based on what it looks like, which is a seesaw. And I am not making that up. So this is a seesaw geometry. That's the shape of this thing. Again, chemists like to kind of name things pretty literally, so it looks like a seesaw, so we're naming it a seesaw. Okay, now let's go to 3 bonded atoms and see what that looks like. So let's use chlorine trifluoride as an example. So 3 times my 7 from my fluorine plus another 7 from my chlorine gives me 28 electrons to work with. So I'm going to put my chlorine at the center because that comes first. So in terms of, which one is going to be my central atom, they all have the same. But if I have more of these guys and I start the compound with this one, then in general it's going to be your central. So our Lewis dot structure puts these things at cardinal directions. I've used up 6 in doing so, which gives me 22 electrons left over. 2, 4, 6, 8, 10, 12, 14, 16, 18 that I've used up, which means I have 4 more left over. I'm going to put them on my central atom then. Here's one here, and I'm just going to stick this other one here, and kind of highlighting my lone pairs with bubbles. So now I've used up all my electrons and I've none left over. So in my accounting, I have 3 atoms, 2 lone pairs, which gives me 5 electron pairs total. So I know that I have trigonal bipyramidal geometry still, but I need to figure out the shape of this thing. So I've already gotten rid of one of these guys. So is it going to make more sense to get rid of an axial one and give me this guy, or would it make more sense to get rid of an equatorial one and give me this guy? Well, I don't know if you can really tell, but it ends up being that we get rid of another equatorial one, so another one part of that trigonal planar slice that goes through. So what I'm left with is now a planar molecule that looks like this. So I'm going to draw it like that, exactly like that. And I'm going to draw it like this, with the lone pairs coming in and out of the plane of the page. With my trigonal pyramid there. Okay, so if we look at this thing, we can see that it has 90-degree angles. And again, because we're not very creative as a bunch, the name of the shape of this thing, it has trigonal bipyramidal geometry because there's 5 electron pairs. That shifts things around in space to give us this particular molecule shape, and we call it a T-shaped molecule. Again, I kid you not, it is T-shaped. Okay, so now we're going to go to 2 atoms. So we're going to use xenon difluoride here. So we have 8 from xenon and 14 from our fluorines, so that gives me 22 electrons total. We're going to put xenon at the center because it comes first. So we're going to do our Lewis dot structure. We've used up 4. Gives me 18, 2, 4, 6, 8, 10, 12. Gives me 6 electrons or 3 pairs to play around with. So I'm going to put all 3 pairs on my central atom because my fluorines are already taken care of. And now I have 2 atoms. If we're doing an accounting to figure out what our geometry is, we have 2 atoms, 3 lone pairs, which means that we still have 5 electron pairs. So we still have that trigonal bipyramidal VSEPR geometry. But now I'm going to get rid of this last one because the furthest apart these things can be is on the opposite ends of that central atom. And now what I have left over is just a linear molecule. And again, here's my lone pairs. So that shape for 2 bonded atoms and 3 lone pairs is linear. So there's your options for trigonal bipyramidal geometries. So we have trigonal bipyramidal geometries, these 4 different shapes that are possible, and it's because of the geometry that it causes these to act in this particular way.